Alright, welcome back to Math and Beats. Today we're going to do a video on introducing what the domain and range of a function are. So here we go. We're going to start with the example you see on the screen. We are given a function big F. Here is the collection of ordered pairs that we see. The ordered pairs being 1, comma, -1, -2, comma, 3, and 4, comma, 0. So what we're going to do first is what it says. We're just going to list the inputs. So remember, the inputs are always the first coordinates of the ordered pairs in the function. So those are our inputs. What are those inputs? 1, -2, and 4. All right. Now we're going to look at the outputs. Let's list them. The outputs are always the second coordinates in your ordered pairs. Here we have the outputs -1, 3, and 0. So that's nice. That's great. What does this have to do with domain and range? Well, this is supposed to help us kind of foresee what domain and range are. Ends up, domain and range are just the sets of the inputs and outputs of a function. So in that part A there, when we listed the inputs, if we went ahead and actually wrote it as a set, the set 1, comma, -2, and 4, that set is our domain of the function here, f. We can also write that as domain of f or d sub f. Correspondingly, the outputs, if we wrote those that we listed as a set, -1, 3, and 0 as a set, that set is our range of the function big F, or if you prefer, range of f, or r sub f. So, say, okay, that's great. Let's actually write down what the domain and the range of a function are in general. So here we have given to us the definitions. If we have a function y equals f of x, the domain of the function is the set of all allowable inputs which define the function's outputs. What do we mean by allowable? We mean input values for which when we plug in and we actually get an output value. So it could be that there's some input value that we plug in and there is no output, and in that situation we wouldn't include that input value in the domain. So it's the set of all allowable inputs. Range, likewise, is the set of all the corresponding output values, which are the result from applying all the domain values here, x values, and then if we apply the output to all, or we apply the rule f to all the input values x, we get the outputs, and all of those outputs as a set is our range. So in the past we've seen diagrams where we draw two little oval looking things. We say, okay, we take our inputs and then we map them. We get some output by applying the rule f to it. In that picture, y being f of x. Then that collection of all those x's on the left, that set is our domain values, and on the right, that set are our range values. So it's all the inputs as a set, domain, all the corresponding outputs, the set which we call the range. So now we should probably look at an example. All right, down here we have an example. In this example, we have 3 different functions given to us, and in each of them we want to state the domain and range for each of the following functions. In the first one, we just have a set G given to us, a set of ordered pairs. It's very much like the example we looked at earlier. So here, we just pick out the inputs, the domain of G here, which we could also write, again, as d sub G, is just the set of all the input values we see, which are -1, our friend pi, and 0. All the first coordinates here. Those are the only inputs. Likewise, all the range values, so the range of G, or R sub G, is going to be the collection of all the corresponding outputs. Here, those outputs being 1, 2, and -5. So those two sets there are our domain and range of the function G. We'll switch colors real quick. Okay, now in parts B and C, we actually have symbolic representations of functions given to us, so we're going to have to think a little bit. And moving forward, I should say that for all of our functions, we assume that they are real valued functions. That is, inputs and output values are going to be assumed to be real numbers for the time being, because if we have some other valued function, it ends up it's a lot more complicated, such as like complex numbers, for those of you who know what that is. So we're always going to assume real valued inputs and outputs. So having said that, here we have the function in part B. Y is k of x. K being the rule is take the input x and multiply it by 2. That's it. So you think of, is there any real number x for which when you multiply it by 2, you get something that is not a real number? And the answer to that is no. Every time I take a real number x and multiply it by 2, I still get a real number. So what that means is all real numbers are inputs, because there's no real number that when we plug in does not define an output. For that reason, we can write that the domain here of the function k, or d sub k, is all real numbers x, or if you prefer to write it as the symbol r, as you may have seen, or in interval notation, negative infinity to infinity. So that's our domain. Hopefully that's pretty clear. And what about our range values? Well, you think, okay, we can plug in all real numbers and it's going to define the function. So if we go way down to negative infinity, for instance, as x goes to negative infinity, then what happens to our outputs? Well, they're being multiplied by 2. So you're just going to get giant, large negative numbers as well. And so the function here, the outputs, they're also going to go to negative infinity. And then we move upwards towards 0 from negative infinity. You know, you're multiplying negative 2 by 2, negative 1 by 2, 0 by 2, 1 by 2, and then you just keep doing that. You go all the way up to towards infinity. Well, now we're multiplying giant, large real numbers by 2, and so they're just going to also be giant, large real numbers, getting bigger and bigger the bigger we make our inputs. So as x goes to infinity, the output y also goes to infinity. So that tells us that the range of this function k here, or r sub k, is also all real numbers, negative infinity to infinity, using interval notation. Hopefully that made sense. Now in part C, we have a square root involved, and we know something about square roots. We know that if you have square root of something, say it's square root of smiley face, well, that tells us that smiley face has to be bigger than or equal to 0. In other words, you can't take square roots of negative numbers. You can, but they are not real. So for instance, if I took square root of negative 1, that's not a real number. Ends up that it is a complex number, and again, we're assuming only real valued functions. There's no number such that when I multiply it by itself, I get a negative 1, which is real. So that's a whole different discussion, which we will have another video on at some point. That is complex numbers. So here we cannot have anything inside the root be negative in order to be defined to be real. That means we got to take what's inside the root. Here it's a plus 3, and that has to be not negative, so it has to be positive or equal to 0. We can simply solve this inequality, and we get a is bigger than or equal to negative 3, and there you go. Any real number that's bigger than or equal to negative 3 will work for this function here to be defined. Hence, we get that the domain of w, or d sub w, is going to be negative 3 to infinity, and we include the negative 3, hence we use the bracket in our interval notation. If you forget about interval notation, we'll have another video on that at some other point. Finally, the range of W here is the corresponding outputs that we plug in. We know something about how square roots act as their inputs get larger. Square roots get bigger as their inputs get larger. Just think of it. Think of, oh, I had to take square root of 1. That's 1. Square root of 9. That's 3. Square root of 25 is 5. So as I plug in larger and larger values into my roots, I get bigger and bigger outputs. The outputs grow, so this function is going to grow to infinity as I plug in larger and larger input values. Now the smallest value is going to be at the very left-hand side of the interval for our domain. That's going to occur when a is negative 3. So if a is negative 3, w of negative 3 is square root of negative 3 plus 3, which is square root of 0, which is 0. So you may recall also square roots cannot be negative as an output unless there's some coefficient of a negative in front, and that's by definition of a square root. So that also tells us now, finally, that our range of W here is going to be the set. Smallest value is the output is 0, and it grows to infinity. So there we go. All right, so that's about it for the video. This video was on introducing the concept of domain and range. The domain is the set of all allowable inputs which define the function as an output, and the range is that corresponding collection, that set of output values that is the result from applying all of the input values. Excuse me. Yikes. Finally, down here, we look at a couple of examples where one was just a collection of ordered pairs, and the parts B and C here being symbolic representations. How do we find those domains? So we'll see further examples of domain and range, and basically most other videos, as domain and range are big topics in describing functions in general. So so yeah, that's about it, and we're done. Math and beats. I hope you learned something. I hope the video helped. Like it, subscribe it, tell your friends about it. Jump up and down, wave your hands in the air like you just don't care. Haha. Anyways, I'm out. Now, time for beats. Later.